just a quick video demonstrating how we can implement the stack data structure in an array. For now, we'll try to stay language agnostic. I'll do a C implementation next. Click the link at the top if you need a full description of this. For an array implementation of a stack, we need the array to hold the data in our stack, and we position the data so the bottom of the stack, the thing that has been there the longest, will be in position 0. In order to keep track of the current top of the stack, we use an integer to track that position. I've drawn an array for a stack here. I know I said I'd try to be language agnostic, but I've made this array start at 0. Everything I'm going to say still works if the array indices start at 1. We just have to manage stack top a little differently. I'll try to point that out where it matters. Let's look at the 4 operations a stack requires. Creating a new stack requires that we allocate the space for the stack. Since it's an array, our stack has a maximum number of things that it can hold. We'll need to worry about that when we're pushing things onto the stack. Stack top should always point to right below where the next entry would be pushed. If the stack isn't empty, that will be the position of the top item on the stack. If it is empty, it will be right below the first position of the array. So, if array indices start at 0, we'll start stack top at -1. So -1 means the stack is empty. And when the stack is full, stack top will be the size of the stack minus 1. If the array indices start at 1, then we'll start stack top at 0. 0 means the stack is empty. And when the stack is full, stack top will be the size of the stack. Push is the operation that puts a new element on the top of the stack. The first thing we need to do is check to make sure that the stack still has room. If it doesn't, we'll have to report a stack is full error. If there's room, we increment stack top and store the item in that position of the array. So, right now, this stack is empty. Let's push a 42 onto it. We increment stack top, making it a 0, and store a 42 in position 0. Done. Let's do it again. This time, let's push a 16. Again, we increment stack top and put the 16 in position 1. If we do that a few more times, when the stack is full, stack top is 6, which is the size of the array minus 1, which is exactly what we predicted for how we would know that the stack is full. So, push put things onto our stack. Pop is the operator that gets the top thing off of the stack. When we are popping, the error that we have to worry about is that the stack is empty. If there's nothing to pop, we can't pop. Since my stack is indexed from 0, stack top being -1 signals that it's empty. If there's something to pop, we have to remember what it is, decrement stack top, and then return the thing that we remembered. Yes, I could do this in fewer lines of code with this strategy, but that always leaves me confused about where stack top should be. I really like that the first solution pops what is at stack top, not what is at stack top plus 1. So I'm going to hide that alternative again. So let's pop the first thing. I'll remember the 64, decrement the stack top, and then return the 64. If we do it again, I'll remember the 17, decrement the stack top, and return the 17. If we keep doing this, we get everything back up to the 42. At that point, the stack is empty, and we know that because stack top has become -1 again. So that's the language agnostic explanation of how stack operations work when your stack is stored in an array. When you go to build this, there are some things that you'll have to deal with in a way that your language supports. In particular, different languages are going to have different strategies for how we pass information into these functions and how we get the results back, and different ways of dealing with how to report the errors to the caller.